my dissertation is on cognitive supports for analogical reasoning in rational number understanding. A central question in developmental psychology, or so-called the Plato's question, is how do we learn so much from so little? From limited experiences with utterances, how do we learn a language? From only limited experiences with animals, how do we learn taxonomy? And also from only limited experiences with a limited number of numbers, how do we understand the meaning of a potentially infinite number of numbers on a continuous mental number line? Well, analogy might provide an answer to all these questions. Analogy involves using knowledge from one situation to understand another situation through the common relational structure that shares among the constitutive elements in each situation. It is a very powerful learning mechanism for cognitive development because it can bootstrap learning far beyond what the input provides. It also widely used in science and everyday life. For example, William Harvey proposed that a heart is like a water pump because a heart and a water pump shares the similar structure that increase of the pressure to the system also increase the flow. From there on, William Harvey proposed a very productive scientific model of explaining the blood circulation. And through this analogy, people have this intuitive grasp of how our heart works. And also they have a new, more abstract understanding of how a pump works. This more general, abstract representation of how a pump works is what we call the schema in psychology. Schema is a form of knowledge representation that binds the relation of the pairs in the system. By having this schematic representation of what a pump is, when we encounter new exemplars of pumps in the future that look nothing like what we've ever encountered before, we can use our knowledge structure of what a pump works to imply and know about how these pumps works in the novel situation. So schema abstraction facilitates analogical transfer, but schema abstraction also requires cognitive supports. According to the structure mapping theory, comparison between a target domain and a base domain can highlight the one-to-one correspondence between each element across two domains, and therefore facilitating the abstraction of the common relational structure, and therefore facilitating the analogical transfer when the same structure were observed in a novel situation. Comparison indeed facilitates schema abstraction according to extensive experimental evidence. For example, when college students are asked to read two scenarios about a negotiation case, both of the scenarios share the same converging negotiation strategy, but they describe two different domain knowledge. Students were asked to read those two cases and describe the solution to examine their schema of this converging negotiation strategy. And after that, they are asked to solve a third case where the optimum strategy would be the same strategy we use in case 1 and case 2 to see whether they can do this analogical transfer. Students were randomly assigned to one of the two groups. The comparison group read the two cases on one page, and they are prompted to think about the similarity between two cases before they generate this schema. In the separate group, participants read case 1 and case 2 separately one by one, and they also need to solve a novel case. Researchers has found that comparison leads to a better quality of schema generation compared to the separate group. Also, this schema quality also positively predicts the likelihood of using the same converging negotiation strategy in the novel situation or the analogical transfer. In this dissertation, we propose to use number line as a schema of the number system because it can represent the relation of numbers. For example, when we point some objects to count, we can represent the relation in the temporal order of finger pointing to objects. We can also represent an increase or decrease in the serial order of the count list, 1, 2, 3, 4, 5. And also an increase or decrease in the quantity that it represents. These all different kinds of relations can be mapped onto each other and onto our mental number line. This kind of mapping takes time. Young children often have very vague representation of numbers, and they will just associate little with small numbers and a lot with large numbers. And it takes development and education for children to form a extending linear structure of the number line. Now the question is, how can we use this number system to support numerical understanding and reasoning? All right, previous studies show that a number line can be used to help children learn large numbers. Alignment between small and familiar numbers and large and unfamiliar numbers lead to better representation of large numbers that they never encountered. For example, 15 on a 0 to 100 number line goes to the exact same place as 1,500 goes on 0 to 10,000 number line. By this kind of comparison, children can develop a better understanding of the decimal system and thus have a better understanding of the large integers that they have little experience of. And we wonder whether or not we can use number line to teach children about fractions, because fractions are pretty important. Fractions are the gateway to college prep courses like algebra, thus the gateway to college entrance and college earning. Despite the importance of fractions, fractions are also pretty difficult to understand. One huge difficulty lies in understanding fraction is overgeneralization of the properties of the integers. This representation of the integer components of the fractions can bias people to have a holistic representation of the fractional magnitudes. And this confusion has good reasons because there's this cross-mapping between integers and fractions. When you look at the numerators of the fractions, the value of the fractional magnitude increases as the numerator increases, just like integers do. But when you look at the denominators, the value of the unit fractions decreases as the denominators increases as a power function, x to the -1. Therefore, early research on fraction understanding suggests that our innate number sense evolved to handle discrete quantities, thereby rendering the concept of fraction number counterintuitive. And we wonder how to build fraction knowledge on our already superior pre-existing integer knowledge. Our overarching aim for this dissertation is to apply what we know about analogy to math education. And through a series of 5 studies, I aim to first look at how well children's mental number line representations are, and thus comparing integers and fractions on number lines help children to have a better understanding of fractions. On studies 3 and 4, we further look at whether the quality of number line representation facilitates explicit analogic proportional. And in study 5, we finally look at whether number lines also aid adults to increase their numerical reasoning. So first, how well are children representing integers and number lines? And how do it develop with age? We ask 177 3rd to 5th graders to estimate fractions and integers on number lines. Those fractions and integers are proportional equivalent, and we ask where does this number go, and children will just mark on the line to denote their estimates. Or we gave children a mark on the line and ask them what number goes here, and they will produce that number for us. Despite the number line task, we also ask children to complete a comparison task where they need to choose the larger one amount between two fractions, and also a ordering task where they need to order three fractions from the smallest to the largest. Then how does children's representation of integers and fractions develop? Here I'm presenting the percent absolute error as a function of the increase of grade. Percent absolute error is mainly a measure of how deviate children's estimates are from the correct value. So in general sense, it measures how erroneous children's estimates are. The lower the bar, the more accurate children's representations are. So I'm presenting children's errors in the position to number test and number to position test. Red denotes integer representation, blue denotes fraction representation. As this plot shows, we find fewer errors for integers and fractions, fewer errors as grade increases, and also an interaction effect between format and grade, revealed by the advantage of integer format over fraction format decreasing with age, suggesting that children develop a more coherent representation of integers and fractions with education. And we want to further quantitatively measure this representational coherence mathematically. So we developed two novel measures. One is the integer fraction correlation measure, which measures the correlation between the estimates of proportional equivalent integers and fractions. So basically, the larger the integer fraction correlation is, the more coherent children's representation between integers and fractions are. Another measure we use is the integer fraction discrepancy, which is the absolute difference between the estimates of proportional equivalent integer and fractions. Basically, the larger integer fraction discrepancy is, the less coherent children's representations are. Then how does this representational coherence develop over age? Well, I'm presenting the integer fraction correlation measure as a function of age on the left, and integer fraction description on the right. So here's what we found. Integer fraction correlation increased with age, and integer fraction discrepancy decreased with age, as what we expected, suggesting that children develop a more coherent representation of integers and fractions with education. And moreover, we want to know, what does it mean that children develop a more coherent representation? So we test whether or not a coherent representation predicts better fraction proficiency measured outside of the number line task. To do this, we submit integer fraction correlation on both type of number line task and controlling for grade to predict accuracy on fraction comparison task and fraction ordering task. And we found a positive correlation between the integer fraction correlation measures and accuracy of both tasks, suggesting that the more coherent this representation is, the more accurate children are in comparison and ordering. We conduct the same analysis in parallel for the integer fraction discrepancy measures, and we found that they have a negative correlation while controlling for grade, suggesting that the more discrepant children's representations are, the more accurate, the less accurate the children's accuracy in comparison and ordering. So in general, the study one shows the developmental trajectory of integer and fraction estimates, revealing through development, children's presentation of integers and fractions becoming more coherent over time. And this coherency independently predict fraction proficiency, suggesting the educational importance of building a coherent representation of numbers. Then the question is, would comparing the values of fractions and integers on number lines improve children's understanding of fractions? So here goes our.
Can I ask a quick question?
Yes, sure.
Can you disentangle the effect of education versus brain development?
No.
Okay.
Thanks.
Well, probably given your age group, group's brain development is pretty negligible at this point.
Okay. That makes sense, right? Okay, so in study 2, we want to know whether or not comparing integers and fractions on number lines will help children to develop a better understanding of fraction knowledge, just like how previous studies increase children's representation of large integers. To do this, we hypothesize that alignment between integers and fractions on number lines help reduce a two-part relation to a single position that has a real magnitude, so that children can use their pre-existing integer knowledge to bootstrap an understanding of fractions. To examine this hypothesis, we conducted an educational intervention with 100 to 5th graders using a pre-test, training, and post-test design. During pre-test and post-test, children estimate fraction and integers on number lines just as what we did in study 1. During training, children were randomly assigned to an alignment group and a no alignment group. In the alignment group, children see 4 couples of number lines, one on the top and one on the bottom, of course, 4 screens for each trained magnitude, so that they have a chance to compare integer and fraction number lines. For the no alignment group, children viewed 8 lonely number lines. All the number lines are exactly the same as the alignment group, except that they are presented one at a time and also in a randomized order. In neither condition were children told to explicitly compare problems, nor did they receive any corrective feedbacks. And we also include a group of college students to see how well we ultimately want children to achieve. So what did we find? Here, I'm also presenting the percent absolute error. The lower the bar means the more accurate children's representations are. Of course, 4 different types of number line estimations: fraction, number to position, position to number, and integer number lines. So here I'm first presenting the children's errors in the no alignment group. And then this gray line indicates adults' performance. And now, very surprisingly, we found that children made more errors than what adults can do. Now, the question is, are children in the alignment group perform better than children in the no alignment group? And are they as well as adults, ultimately? And what we found is that, yes, children in the alignment group are better than the no alignment group for both their fraction estimates and also for their integer estimates. Alignment worked, and it not only improves a fraction domain's knowledge, it also improves the integer domain's knowledge as well. Then the question is, can the training effect transfer to post-test where the analogical resources are not available anymore? So we conduct a similar, the parallel analysis with percent absolute error of children's estimates in the post-test. And we observe similar results pattern, of course, for test, suggesting that the training effect persisted at the post-test when the analogical sources of integers desisted. So across these 2 studies, we found that a very short 1-session alignment with integers and fractions and number lines leads to better understanding of fractional magnitudes understanding, suggesting that comparison does facilitate abstracting the schema. And this schema means fractions and numbers that denote magnitudes and can be placed on number lines. Now, the next question we want to further explore is whether or not magnitude knowledge in turn can facilitate explicit proportional analogy. And this is a bigger question related to the debates on the development of analogical reasoning. There are mainly 3 debates on explaining how we develop analogical reasoning skills. The first account is the knowledge acquisition account, emphasizing the role of familiarity in the relational reasoning. For example, when children are asked to perform these classical 4-term analogy questions, a half of a circle to half of a rectangle is to a quarter of a circle to what? And children were presented with these 5 options to choose from. And the correct answer for this question is D, because it shares the maximal structural similarity. And researchers have found that children with better proportional knowledge are better at conducting this relational reasoning questions, suggesting that knowledge of the terms matters. Yet another account suggests that the executive function account says that the role of executive function also cannot be ignored in this sort of case, because children need to choose between a relational match among several perceptual match, and they need to inhibit the tendency of choosing perceptually very similar to one of the terms. So this task is not that well designed to rule out the possibility that the development of analogical reasoning is due to the maturation of executive functions. Yet another account suggests that analogy is more about this domain generability of pattern completion. When children are faced with this kind of questions, they first extract the relation among A to B and then apply this in context independent relation to term C so that they can generate term D. So the current research wants to further investigate whether there are any conceptual prerequisites for analogical reasoning. To do this, we investigate the development of a very simple four-term analogy questions, where we ask children to fill in the blank, 9 tenses to 1 as 9 is to what, with the four-term structure readily available for them. And all they need to do is to fill in the missing component from this structure aligned, vertically aligned them already. So we ask participants from varied education to complete this kind of task. We ask college students, adults recruited from MTurks, and 3rd to 5th graders to see how they perform this very simple fraction analogy questions.
What are mechanic Turkers?
It's Amazon mechanic Turkers. We can ask for their help to fill in some psychological survey through Amazon, and they can get a small amount of payment by participating in our survey. Mainly it's a participant recruitment platform for us to.
Totally. Okay.
Thanks for asking. Yes, I should have explained that better. Okay, so to see whether fraction knowledge matters, we also designed 3 parallel conditions with other domains like letters, magnitude, and integers. And the main difference across this form is that we replace the label so that we can check whether or not fraction knowledge matters. And of course, all these 4 types of problems, all participants need to do to be accurate on this kind of 4-term analogy question is to fill in the missing part from the structure that is already available for them. So it should be very easy. And according to the relational priming account, if analogical reasoning is totally due to pattern completion, then we should expect participants excel on all 4 tasks. And there will be no difference across problem types in terms of accuracy. So here I'm presenting the accuracy across 4 problem types across the 3 population, like college students, adults, and children. So here's what we found. Fraction accuracy on fraction analogy was still lower than accuracy on other problem types across all age groups. It is even with this alignment between analogical target and source readily available for them, suggesting that this prior knowledge of fraction matters and proportional analogy requires more resources than merely pattern completion. So we further want to establish this causal link and experimentally test whether or not training knowledge of conceptual understanding of fractions can improve explicit proportional analogy. To do this, we again conduct an educational intervention asking 3rd to 5th graders using a pretest training and post-test design. During pre-test, children again estimate fractions and integers are normalized. During training, children were randomly assigned to one of the 3 training groups. The conceptual training groups emphasizes that fractions is a kind of measurement, it's a kind of number that can be used to measure quantities in the real life, like how many chocolate bars Emma ate. To measure something that is between 0 and 1, we introduce a special number cut fractions. In the procedural knowledge training condition, we explicitly emphasize the step-by-step procedure of how to estimate fractions on the number line. For example, where is 9/10 on the number line here? To estimate the position of a fraction on the number line, you can follow 2 steps. First, you multiply the right-hand number by the denominator, and then you simply estimate the numerator. And for the conceptual plus procedural condition, we merge those two training together to see whether there are additive effects. During post-test, we ask children to make some explicit proportional analogy that we used in our previous study. We also include a group of adults recruited from kind of third to serve as a reference group. And here I'm presenting the relation between pre-test estimation errors, pre-test knowledge of magnitudes, and their post-test accuracy on 4-term analogy questions. And we see a negative correlation, suggesting that children who made more errors during pre-test, they're with lower magnitude knowledge, fail to correctly solve the 4-term analogy questions at the post-test, suggesting that magnitude knowledge matters to solving proportional analogies. Then more importantly, we care about whether or not there are conditional differences among 3 training groups, conceptual, procedure, and conceptual plus procedure. So here I'm presenting the accuracy of the proportional analogy across these 3 groups. And what we found is that conceptual training yielded greatest accuracy than the procedure and conceptual plus procedure was, but we did not see an addictive effect for the both training merging together, suggesting that conceptual understanding of fractions facilitate proportional analogy. So study 4, in general, looks, the conclusion is the analogies are not simply due to pattern completion or mere the maturation of executive functions, but it also depends on the knowledge of the terms. And if we use schema-based teaching, we can also facilitate this proportional analogy. So far, we highlighted the cognitive importance of number lines to teach children about rational numbers. But can number lines also help political partisans who are in many aspects like children? For example, like children, political partisans often reason and reach to the conclusion of what they want to believe as opposed to what the evidence is. For example, when they are giving fictional data on the effects of gun control on crime, people with high numeracy skills often tend to only use their numeracy skills and correctly solve the data interpretation question when the true interpretation confirms their own political beliefs. And we find this scenario very interesting, and we think a key obstacle here may lie in people's trouble with fractions, because to successfully solve this question, you cannot just simply complete the absolute error on a single row, but you need to compute the proportion across these 4 cells and reach to the correct solution. So we wonder whether number line can increase accuracy and help participants to perform better on this kind of tests where they typically perform really low. So to do this, we asked 1,000 adults to first measure their prior attitudes towards these kind of political controversial issues. And then they completed a covariance task, as I just presented. They were randomly assigned to a political controversial situation, asking about the effect of gun control on crime, or a politically neutral situation, asking about the effect of a new screen cream on rash getting better or worse. For half of the participants, we switched the labels so that the true interpretation can be either way. And to also looking at the effect of the format, we asked participants to solve 2 problems, one in the table format and one in the number line format. The order of these 2 format presentations are counterbalanced across all participants. And we want to see whether number line presentation can help participants to more objectively reason about political controversial issues. After that, we measured participants' numeracy using a 9-item numeracy scale. And finally, they reported their political outlook. And what we find, can number line increase accuracy? Here I'm presenting the mean accuracy of the first trial participant completed in the table format and in the line format. And we found that number line did yielded greater accuracy than the table format. And this general pattern is also observed across all the different subgroups, across politically controversial problems and also politically neutral questions, across conservative and of course liberal, and of course whether or not their true interpretation affirming or disaffirming their political outlooks. And finally, we want to see whether this number line can be education and whether learning from number line can transfer to the table position, to the data presented in the table format. And we did find an interaction effect between the format and the number of trials, suggesting that solving the table problems after solving the number line problems yielded greater accuracy compared to solving the table problems first. So if we compare this point and this point together. Okay, so generally across all 5 studies.
Can you go to the previous one and
Yes.
repeat your interpretation, please?
Yes, this solid line means people solve the line problem first, and then they solve table problems in the same scenario. And this dashed line means people solve the table problems first, and then solve the line problem afterwards. So this point means the first question people solve is the table format, and this point means the second problem people solve is a table format, which is after the line format. And we can see this point is higher than this point, suggesting that if people solve the table format after the line format, it increases the accuracy. I know I kind of rushed through the explanation. Thanks for checking. Okay, so across 5 studies, we found comparison leads to schema abstraction, schema quality effects, explicit analogy, and finally, number line can be a helpful schema to facilitate numerical reasoning. In general, we find number line can be a very helpful tool, a mathematical schema to facilitate both the development of fractional understanding and analogical reasoning. And finally, it has many educational implications as well. Rather than integer being an obstacle to fraction learning, pre-existing integer knowledge can be a stepping stone when instruction draws on the power of good analogy. And also, if scientists working on politically controversial questions wish everyone to understand their data, presenting data in the number line format is likely to be beneficial. Finally, I would like to thank my advisor, Professor John Opfer, and all my collaborators and founders, and all my emotional and social support in Columbus over the past 6 years. Thank you all so much for being here and for listening.